Now we're going to solve question 2 of the 2018 midterm. In the previous video, I solved part A and part C, and that's using node voltage analysis. Now I'm going to solve part B and part C using mesh current analysis. And in the end, what we're going to want to do is find the node voltages VA, VB, and VC. But we're going to be using the mesh currents first, and then we're going to solve for the node voltages. So now, when we're doing mesh current analysis, so we're going to do part B right now. And so these are, part B is to develop the mesh currents, the expressions for the mesh currents. So we have to identify them. So we're going to identify this as the I1 mesh current, I2 mesh current, and the I3 mesh current. So now let's do mesh 1. Okay, now what's interesting about the mesh 1 current is that there is a branch that has a 3.5 amp current source, and that branch is only shared by the I1 mesh current. So I1 must be 3.5 amps. However, we see that the current directions are in the opposite direction, so the current source is pointing down, and then the mesh current is going up, so we have to use a minus sign. So I1 is equal to minus 3.5 amps. Okay, let's do mesh 2. Okay, well, we see a similar situation for mesh 2. The 2 amp current source is in a branch that's only shared by the I2 mesh current, and they're both in the same direction, so we can write I2 directly as 2 amps. So now let's consider the I3 mesh current. So we see that this one is more complicated, and it has branches that are shared with other meshes, and there's no current source to give it a specific value in its own branch. So we have to do the equation for it. So let's do mesh 3, and then the equation. Okay, the equation is going to be basically KVL. It's going to be a loop equation, and we're going to develop expressions for the voltage across each component. So now let's do the voltage across the 3 ohm resistor. So using Ohm's law, we have 3 ohms times I3, and that's the only mesh current, so that is the voltage across the 3 ohm resistor. So now when we move on to the 4 ohm resistor, that's a bit more complicated because there's 2 mesh currents and they're in opposite directions, and how we write the expression for that, or the term, is going to be 4 ohms times, now it's going to be the I3 mesh current, so that's the 4 times I3 is going to be the voltage across the resistor just for the I3, and then since the I1 mesh current is in the opposite direction, we say minus I1. So if we did 4 ohms times I1, we'll get the voltage just across the 4 ohm resistor just based on I1, but it's in the opposite reference direction. Okay, so then now let's do the 2 ohm resistor, and we see that there are 2 mesh currents associated with it. So we have 2 ohms times I3, and then I2 is in the opposite direction, so we say minus I2, and that's equal to 0, and that is because of KVL. Okay, so now we've done part B, and the answers, well, we have expressions for each of the mesh currents. Okay, we have the I1 mesh current, the I2 mesh current, and the expression for the I3 mesh current. Okay, so now let's move on to part C and find the node voltages. However, before we do that, we are going to have to find the numerical value for I3. So we're doing part C now, and that is find the node voltages using mesh currents. So that's the thing that we're doing right now. Okay, so we have to find the I3 mesh current. So what we can do here is we can label these equations. So we can call it equation 1, equation 2, and equation 3. Okay, so now what we're going to do is we're going to substitute equation 1 and equation 2 into equation 3. Okay, and when we do that, we get 3I3 plus 4 times I3 minus 3.5 plus 2 I3 minus 2 is equal to 0. And then we simplify 3I3 plus 4I3 plus 14 plus 2I3 minus 4 is equal to 0. Then we have 9I3 is equal to minus 10. And then we finally get I3 is equal to minus 10 over 9 amps. Okay, so now we're going to use the mesh currents to solve for the node voltages. So now, knowing the node voltages, knowing the mesh currents, we can solve for the node voltages. So we have, let's do VC first. And so what we have is a circuit that looks like this. We have VC connected via a 3 ohm resistor to the reference node. Okay, and what we know is that there is an I3 mesh current moving in this direction, or in this direction, and with a value of minus 10 over 9 amps. Okay, and then when we solve for this, we are going to get an expression. Let's just maybe make it a little bit more explicit. What does it mean? It means that we have a VC like that. That's what VC, the value of VC, that's what it means in the circuit, with a VC across the resistor with the polarity given. Okay, that's just to make it a little bit more clear. So then when we solve for it, we see that the current is going in the opposite direction of the voltage drop that it normally would, so we have to use a negative version of Ohm's law, so it's going to be minus, and then the current minus 10 over 9 amps times the resistance, which is 3 ohms, and then VC works out to 3.333 volts. So that is the first node voltage that we solved for, and it is the exact same value as what we got when we did node voltage analysis. Okay, so then let us go to the next voltage, and we are going to do the VB node voltage, and I'm going to do this one two ways. So the first way is easier, more straightforward, but the second way is going to illustrate something for you. Okay, so the easy way looks exactly the same as the previous example. We have a resistor connected to ground, so we have VB here. In this case, we have a 2 ohm resistor. The twist on this one is that we have two mesh currents, so we have an I2 mesh current in this direction. I2 has a value of 2 amps, and then we have I3 in this direction, and that is I3 is equal to minus 10 over 9 amps. And when we are solving for VB, we are solving for a voltage like this. So it's going to be VB like this. Okay, that's what that means when we say VB. Okay, so let us develop the equation for VB. So VB, and let's say we consider the 2 amp source, it's going in the opposite direction of the voltage drop, so we have to use the negative sign. So it's minus 2 amps, okay, times 2 ohms. And then we have the I3 current, and it's going in the correct direction of the voltage drop from high to low, so we use a positive, and then the value is negative 10 over 9 amps times the resistance, 2 ohms, okay? And then this works out to what? Minus 20 over 9 volts, okay? And then that works out to minus 56 over 9 volts, and then in the end VB works out to minus 6.222 volts. And that is our second result, and that is exactly the same that we got in node voltage analysis. So now let's do VB in an alternative way and hopefully illustrate a little bit more tricky way of analyzing it. Okay, so VB alternative, right? Alternative method. Okay, so what we're looking at here, oh, I spelled alternative wrong, so let's just fix that. Alternative method. Okay, so what we're looking at over here is a circuit that looks like this. So we have VB up here. We have the resistor, which is 4 ohms. And then we have VC down here, okay? And we know that VC is equal to 3.333 volts. Okay, and then what we're going to do is we're going to develop an expression for V4 ohms. That's the voltage right across the resistor. And then what we can do is develop an expression for VB. So VB is going to be equal to V4 ohms. Let's make that a little neater. V4 ohms plus VC. Okay? So that's going to be our basic equation. So now what else do we know in this circuit? We know the mesh currents. Okay, so we have a mesh current going up, and its value is it's the I3 mesh current, and its value is minus 10 over 9 amps. Okay, and then we have going down the I1 mesh current, so that's I1, and that's equal to minus 3.5 amps. Okay, so that's what we know. So let us write the equation that describes this system. So we have VB is equal to, and now let's write in terms of the mesh currents. We have this I3 moving in the opposite direction of the voltage drop, so we have to use the negative version of Ohm's law. So it's minus, and then the current value is minus 10 over 9 amps times 4 ohms. And now we'll do the I1 mesh current, and that's going down in the correct direction of the voltage drop from high to low, so it's going to be plus, and then the current value is minus 3.5 amps times the 4 ohm resistor, and then we have to add the VC voltage, right? We can't forget about the VC voltage, so we have to add that in there too. It's like an offset, so plus VC, and we know that that's equal to 3.333 volts. Okay, so let us simplify, and we get 40 over 9 volts minus 14 volts plus 3.333 volts, and that works out to VB is equal to minus 6.222 volts, which is exactly the same as what we got in the last example, doing VB in a simpler way, and also the same as what we got for the node voltage method. Okay, so now let us do the last one, which is VA. Okay, so now this circuit looks the same as, or similar to our last example. So we have VA up here, we have a 3 ohm resistor, and we have VB down here, and we just solve for that, right? It's minus 6.222 volts, okay? And then let's just denote the voltage drop across there. So we say that that's V3 ohms, okay? And then we're going to know that VA is going to be equal to that voltage drop, V3 ohms, plus the voltage down here, VB. Okay? So now what else do we know? We know the mesh currents. Okay, we know going in this direction we have I2, and that is equal to 2 amps. And then going down we have I1, and that is equal to minus 3.5 amps. Okay, so it's a little cluttered there. Let's just tidy that up. 3.5 amps going down. Okay, so now we can write the expression for this circuit. Okay, let's maybe tidy this one up a little bit too. Okay, there. So VA is going to be equal to, okay, now let's write in terms of the current. So let's consider I1. So it's going in the direction of the voltage drop for the resistor, so it's going to be positive, but the actual numerical value is negative, so it's going to be minus 3.5 amps times 3 ohms. And then now I2 is going in the opposite direction of the voltage drop, so it's got to be negative, and its numerical value is 2 amps, and then the resistor is 3 ohms, and then we can't forget VB. Okay, so let's write VB on here too, so plus VB, and we know that its value is minus 6.222 volts. Okay, so now let's simplify. Minus 10.5 volts minus 6 volts minus 6.222 volts. Add them all up, and we get minus 22.722 volts. Okay, and that is the third result that we're looking for. So that's all of the node voltages. We've solved for all of the node voltages, VA, VB, and VC, and this is the same value as we got for the node voltage analysis. Okay, so now we've used two methods to solve for the node voltages. In the first video, we used node voltage analysis, and in this video, we used mesh current analysis, and then we took another step to actually find the node voltages. So using mesh currents to find the node voltages is a little bit tricky, as you've seen, because you have to interpret Ohm's law correctly in all of the reference directions. However, when we did the node voltage method, the algebra was a lot more tricky. We used Kramer's rule to solve a more complex system of equations. So it really depends on the circuit that you have, which method is going to be better for you to use. So I hope this helps. If you find the reference directions and the polarities using mesh current analysis to be confusing, please refer to our mesh current lecture notes, and there's some insight in there, and of course talk to your professor. Thank you.